snap. I think it's another brief moment in time when we get to see the change of the tides. The shifted, twisted bit technology showcasing the little bits of safety, while the quick trips are surely randomly sparking the photons around me. Let the light flow from the heat, yo. When the photons ignite, highlighting, yo, then you know it's that time when we force a change in tides. A little bit lined with something in us. It's almost like we something else, autonomous, or maybe perhaps it's that missing piece you needin'. Perhaps it's that simple message you searching. Perhaps it's just a different time framing us for the next adventure in the mainframe. Getting excited, so are the photons. Don't laminate so we can change the coupon. Let me raise the hash rate, submit the coupon fake, and reduce the rate while we mine our major bags. Crypto technology like cryptographic money will hashing your life into a set of QRs. It doesn't matter cause it's time for 3D changes perspective. Welcome to the show. Welcome to the show. Welcome to the show.
Well, yeah, welcome to the show, everybody. I'm 3D. Thank you for tuning in. I'm gonna hopefully get that tuned down, or reduced down. It's about a half a minute too long, I'd say. But anyways, thank you all for joining in, saying what's up, and saying hello. I am in the process of getting absolutely everything set up, but while we do that, let's go ahead and let's get into the start stuff with today, because since we're doing a mini-series on artificial intelligence, I just figured we should at least look at the algorithms and at least how they differ, so to speak. So something I've noticed amongst my friends before doing this, especially when I was telling them we was doing a mini-series and I was asking questions and stuff, something that I noticed that kept coming up is that a lot of the people who I knew that were like, they were running algorithms of some kind, and I mean that like as in they were running, especially when I was telling them we was doing a mini. Sorry about that. Sure, that got confusing. But when we were talking, like when I was talking to people and they have services running and they're using them as tools, so they're not just like using these things and putting anything up. They're literally like using these as tools, versus instead of like, you know, just using it for fun. You know, a lot of them are using it for some kind of revenue along, is I guess what I'm also saying. And they come to this point where they eventually ask, why are there so many different AIs? And often they are curious as to like why they work differently. And believe it or not, the reason why some AIs have special name tags, it's now too loud. Wow. Hey, at least that's better than anything. Alright. So, talk to me if it's still too loud. But anyways, some of the name tags like GPT, SD, R1, and Byzine, for example, are all AIs that work differently. The techniques to accomplish the goal is different to get to the same goal. So it's like they use different techniques to accomplish the same goal, just to name a few of them, because there are many more. And so today I would like to change your perspective on exactly how some AIs individually work-ish. And I say it like that because there's only so much breaking down I can do in a short amount of time. We're going to do it with more than one, and so it happens as it happens. But I just want to go ahead and thank today's partnerships. I want to thank DeOrganize for teaming up with Bitcoin Live Digital Broadcasting, DB, because Bitcoin Live and DB and DeOrganize is a paradise combo. I see heights for both organizations. Now, if you haven't checked out any of DeOrganize early morning podcasts for stocks and other topics, then they seem to be taking off with it every day with more and more views. So go ahead and check them out on X, Twitter, and among other social media platforms. Let's go ahead. I want to thank today's sponsor, and also the network sponsor, boom, boom, Shieldfolio. That's right. I want to thank Shieldfolio for sponsoring today's episode from within a quantum bit, as well as the Bitcoin Live DB network. Now, if you haven't seen Shieldfolio or a Shieldfolio, they are a little black book that is made from stone paper, stone paper. And so they're fade resistant, tear resistant, and water resistant. So you know the info and secrets you store in a shield folio will last and survive whatever you throw at it. I personally have a shield folio myself, and I definitely use it for like website info, contacts, crypto keys, among other things. These are like little black books that are pocket sized to be ready at your side, regardless of your adventures online or in real life. And if you look behind me, around me, somewhere there is a QR on screen. You can go ahead and scan that. There's also going to be one on screen throughout the whole episode. You can scan that at any point in time. Go visit their website, grab your folio, and use Bitcoin Live 20 at checkout there to get 20% off your total today. Thank you, Shieldfolio, for sponsoring today's episode, and thank you for Deorganized for partnering with us today. Now let's jump into the jump-ins before we continue on. Sorry, I hit the wrong one. Thank you again, Shieldfolio, for sponsoring today's episode and helping us do what we do. Now, in case you didn't know, I am seeing, for example, I do see your messages, Nick, on YouTube. I am on YouTube and I am on Twitter. I'm hopefully able to actually get comments on both sides, but you guys won't be seeing them on the show anymore. For some reason, I'm having issues getting them to pop on, but at least I'm able to most likely get them on both sides now that I can only see. So I would be answering and talking to you guys live if you're on either X, Twitter, or YouTube watching this. So if you're anywhere else, maybe get to one of those so you can at least check it. It's all the same name everywhere, Bitcoin Live DB. Alrighty then, so welcome to the Greater Photon. Welcome to the Photon of the Greater Fourth Dimension Quantum Machine. It'll help I could read around writing. But yeah, I really like this setup. It is definitely beauty. And we're going to go a little bit further. So throughout the episode, you'll see a little pop-up like this. This is their main screen. This is where we're looking at. And at any point in time, you see something like that QR right over there. You're going to be able to scan that to actually follow along with today's episode. So wherever we're at, that QR will take you there. And so, for example, this is the YouTube channel for Deorganized. And I just want to point out the Deorganized Media. They go live almost every morning, so check them out. Free daily hookup on what's digitally popping. It's a great little show, great things going on. If we click on the live section, you'll see probably a lot more going on in here than on the videos. You know what I mean? Absolutely. Stunning, packed, full of content. Alright, so today we're talking about AI. It's what I guarantee. It's what we're saying. It's what we're doing. So here is the very first episode. Sorry. I have to pause the Twitter thing. It is distracting me. Hopefully the chat still comes through. But anyway, so here we go. Here's the first episode of the AI miniseries. We went over basically catching up on a lot of AI stuff, but basically we went over the premise of AI agents, what they are. We kind of discovered that AIs are AI agents, but people can be agents of AI too. And then we get into the second episode, and right here in this episode, we basically went over or caught up with major AIs like DeepSeek and OpenAI, but also how they're abusing customers. Like you can see right here on the screen, we actually have it at a point where you can see one of the main concerns where they're actually able to kind of basically screw over their customers even when they're offline. So we covered that, then we highlighted potentially FOSS, but at least open AIs, before we at least concluded on one truly open FOSS AI. And it was a beauty of an episode, I must say. So if we go in here, this episode, which was last episode, we went over actually being like, we went over the use cases of AI, like what is it being used for. For example, this picture right here is kind of the main use cases of AI at the time. We did also look over a handful of no-install, web-ready, usable AIs that do practical jobs, like making music, for example. Then we listened to a handful of songs by AI. I wrote the lyrics, and AI did all the rest of the work, and, well, it was fun, but because of that episode, I took it a step further, and I figured let you guys know about it, because why the heck not? We're doing still more about AI. I went ahead and actually, where am I? Yeah, I went ahead and actually made an AI album where all the lyrics are written by myself, and the AI was directed by me, but AI played all the instruments and did all the singing on all of these tracks. BandLab decided and agreed to publish it for 100% for free. You can come here, you can download it 100% for free, or just listen to it. Doesn't matter. It's just for fun. I wanted to make sure you guys understand it's just for fun. Have fun with it, but you know, basically, I just used the tools we had on the previous episode that we used then. I used that to make this entire album, and you know, it's kind of stepping us forward into what's going on today. So like basically today I want to basically add in that, well, not all AIs are the same. Well, we kind of hinted on the search for OpenFOSS AI that the backend or language models was a very important thing. Then we hinted more of the ethical reasoning behind why they're so important. In reality, it goes beyond just how things are labeled. It's also what is labeled into more effects of on top of that. Like I can't say them all. There's a ton of like a just big old long list. Thank you, Rosif. I see your comment. Thank you. So with your that subtle hint that every aspect of AI isn't a clear and cut anything, that's just more gray on gray, my friends. And last week, the last episode highlighted on the brightest gray spots of the spectrum of AI. So today we're going to kind of view the darkest gray spots in the spectrum of AI. And before we go any further, I want to go ahead and give you guys today's free search query. Today is AI algos. That's right. What up, AI algos? A pre-search free query. I think not using the full word algorithms kind of does two things. It looks for the full term normally. It also looks for misspellings. It kind of hits a different part of the algorithm that thinks that you're misspelling something accidentally, so it tries to correct you behind the scenes that you're noticing it. And so that will include a lot more variations of algorithm than you'd be expecting. But it's also going to include more of the short terms because it might consider that you're doing a shorthand, and will also include those like AI and algos both hit the algorithm of the side of the algorithm. So you end up getting more and more. Like if you see, for example, we do have on here like artificial intelligence and types of AIs and algorithms. So we get a combination of both pretty equally with this search query. And again, this is a search query that if you come back to it after today's episode, it will definitely help you out. Most likely in getting more information into this type of topic, which is, well, the things that actually control the AIs that you might even be using today. So I want to go to this page right here. This is Quora. It's a place where people ask questions. And so basically, I think that one of these answers, the one right here in front of me, it kind of answers the elephant in the room very bluntly. So the question basically is, why do we study different algorithms for the exact same task? When, you know, we see there is this top answer by Daniel R. Page. The actual question's above it. We'll get into that later, more on it. But here he says there can be several reasons. I mean, he's not going to list them all. He's going to basically list the top three. Okay. Efficiency. Certain algorithms can be more efficient than other ones, so algorithms may outperform other algorithms in certain situations. You kind of got to test them both to find out. It's just, you can't get there without testing. Historical and theoretical reasons. So algorithms precede other algorithms in their discovery, and since some new algorithms just build off the older ones in either concept or literal base as a basis, and then adding onto, it makes complete sense to show possible simpler algorithms before moving on to more advanced ones. he uses that as a trivial extension for the example, or trivial extension, and then he has an example. It makes complete sense to show the forward focusing algorithm, Wikipedia before Edmund Karp's algorithm, and then he cites Wikipedia again, as all the theory underpinning the former is helpful finding out the latter. Because you have to know how forward focusing algorithm works in order to understand how Edmund's Karp algorithm works, is what he's saying. So, Reddit, usually designing algorithms can be very rigorous venture. So, knowing how to prove an algorithm's correctness or a problem as a certain property as a paradoxical goal, so to speak, or many professors and instructors will show you, basically like seeing how the different algorithms may vary the different techniques to get to that goal, and then being able to ensure that it is actually getting to that goal. So it's just to verify, basically. So you must remember that in designing algorithms is a problem-centric task in research. So sometimes it is a good idea to see how one exploit the properties of a problem to design the different algorithms to employ different techniques behind them. All right. So basically, there's more than one way to solve almost any problem. So there should be more than one way to do almost any algorithm. Yeah, I think is a simple way to put that. But I think it gives you all the words you really need to understand to get. It's a lot. Okay. This is just the top 3 reasons. Now I do have an image of this backup, so we're not going to go over the image. Now, I do believe, like when I was first writing this episode, I think I was originally going to rate or equivalate all the algorithms, and I still kind of want to do something like that, but now I realize I got to make it a lot more simplified. So, I don't know, future episode maybe. Anyways, let me just show you what I found when I was trying to refresh my memory on how many of them are, because I could have sworn there was like 9 or 18 or something like that. Maybe for just searching there's 9 or 18. But then there's optimized searching. And then there's logic. Okay, so my note says to actually scroll down and talk about some of these as we go. So basically, we have various different search algorithms in this first front of words. So basically, there's discrete search algorithms, uniform searches. Those are just different ways, basically, to handle the metadata and correlated data as the output and input. Then you have like brute force searching, which is like just anything and everything that might fit the bill. So it's kind of like the greedy algorithm, is what it's also well known as, but at a much stronger pursuit for knowledge. And then you have different tree methods. We won't get to all of those, but there's different ones. Then you have state space for the searching, which is like the word stating and things like that, but also like a contextual state of your actual search. Then you have informed searches, which are like best fits, ACE search algorithms, heuristic, and pruning based algorithms. So ones that are a little bit more decisive on what you might actually need. Then adversal, which are going to be the minimal and maximum type stuff. Logical, which is going to be for like production systems, ruling systems, forward chaining and backward chaining. So how you go throughout your different logic steps. And then planning as a search, which is like, again, the state space thing, but also like the medium to the end analysis. And medium end analysis is kind of cool because like there's this big thing we kind of talked about, I think last time, where it's like you can stack a bunch of different like models on top of each other to get an average, which will then show you the positive over time if you get enough negatives that are just like poorly done, but some part of it is right. And it's kind of like something similar to that. Not exactly, but it's a good way to put it. We got a lot of these. I'm not going to go through them all, but as we go on, they're just going to take the ones we kind of explained, and we're going to do different things with it. Like the hill climbing kind of takes advantage of some of this, like means, and then this min-max, and then pruning state with best fits. And it might have multiple depths into that and things like that. And I just want to go down because there's, again, a lot of these. So logic AIs, they're actually going to look at things a bit differently. And to be honest, these are the AIs that really got me interested in doing this episode, because logic AIs just seem to get better and better and better the further we go down the line. And you'll see that the more we go down, there's different ways to do this exact same methodology of logical AIs, and I think that's insane. It's not just all in one set. Basically, like every one of these like little indents inward are sets of sets. So programming, you know like that word programming using logic, and then logic programming is the one below it, and then C logic as a search above it, like it's an additional point or whatever. And then you see like forms of logic, and you have these first two. Well, this first order logic also has two more inside of it, and then you have fuzzy logic, which has these inside of it. Then you have default reasoning, which has these inside of it. And so it's like we have this main step, and then we have all these other things that we can do on top of that. And some of these can go on top of the other ones on top of it. So some of these, like I believe the fuzzy logic, you can do fuzzy logic, then the set theory, then the systems, and the kernels, or perpetual in that order, and they will all work together. Or you can mix and match them as long as they keep that order of use top down. So some of these are, not all of them are going to be like that, but a lot of these are. And you see like relevant space learning. Page does not exist. That sucks, because it's a field of study that's like getting stronger and stronger every day. Other symbolic knowledge and reasoning tools. So other ways to do it than probability setups, which is like some of the more original stuff, and the classifiers and strategic learning models, and then actual AI, artificial neural networks, and then biologically based or embodied AIs, and then cognitive architectures. Then we get into stuff that don't really matter. Okay, so a lot here. We ain't going to move them all. We're kind of gonna basically go over my favorites. Sorry to do you like that. We gotta learn what I like in AI browsers. Because I talk a lot about negative towards AI, and it's because I spend a lot of time just playing with AI, and I have a weird understanding of it's just pre-programmed information. I ain't gonna say any other way. So we're gonna keep on going. We're gonna go into major forms of AI. Straight up, like we're about to catch a lot of images. I think that these images that we're about to see will describe a large portion of the maths and stuff we don't really want to talk about. Or in other words, this is a prettier way to view what's going on instead of numbers and fancy Greek symbols. I hope that helps. All right, so formal ontology, I'm saying that wrong. Ontology is what we're looking at. This is basically a decision tree that will basically give us a rule set, and if you were watching some of the previous episodes, you may have seen some structures like this, and it might seem very familiar. So for any entity, it can't, so very top, any entity, it can be a set or an item, as it splits down to. So the separation at that same level shows they are not alike. A set and an item are not the same or alike, but a set can contain multiples of items, so we don't need to break a set down because it's just going to be multiples of items. So we just need to break down an item. Okay, so an item can be an individual or category. Those are not the same, they are slightly different. In other words, individual is a person or like a person, and category is an object or like an object. Now, you would be able to treat these basically the same, except for the point that one is a person or like a person, and the other is an object or like an object. I got to really make sure you understand that. Kind of important there. So, for example, a dog could either be one of these. But say, for example, a dog with a collar, AI might automatically see that as like a person, or, for example, owned by a person, while a non-collared dog may be considered like an object because it may be considered a stray or wild animal. So we break these down as either abstract, concrete, or space-time. So in other words, you could put these down as potentially figurative, literal, or of past or future. Okay? So considerably, these have no differences outside that they are not the same. They are not the same prospectively. Only prospectively are they not the same, like the last two sets. So all of these in this row are broken down the same. This final breakdown is set up to realtor property occurrence or presential. In other words, you could put that as representative, the thing, related to, but not the thing, or being shown to or for. So if you didn't catch it, each of these label breakdowns just describe more of the thing. All of them just describe the entity. For example, let's say the entity was a cup. It could be a set or a single item. In our case, it's a single from a set, but it's still a single item. It's categorically because it's, well, hold on, I lost my point. Categorically because it's not a person or like a person. So I'm saying it's concrete, definitely, because it's, I can touch it and stuff. And depending on if I'm drinking it or not, in terms, like we might say things like, it's coffee, then the cup is figuratively coffee because it contains coffee. It is the thing at times, like when it's referred to as the cup, or even a person's cup, also when it's being referred to as coffee instead of cup. It is in relation to that coffee since it contains the coffee. And finally, referred to as the cup can be shown to me, like just being referred to as the cup being in my view, just being cup in my view, like on my screen, there's a cup in my view. That cup in my view is being presented to me because it's in my view. So the cup can be in relation, it can be all three of those things depending on how you prospectively or objectively are looking at it. Each bubble gives you information as well as allows you for in different ways to be clustered. Very important point. For example, we can explain how a cup of coffee could at any point in time be any of these labels. And if there's a label with coffee cup, table, warm, presence, let me say that again. Imagine there's a label that says the following titles: coffee, cup, table, warm, presence. Now close your eyes. Hear me out one more time, bro. Says here, close your eyes. Let's say that again. Coffee, cup, table, warm, presence. What picture you just get in your head? What scene was just described to you? You may be able to come up with many scenes, including the one right here on my phone. I got one right here. I got a laptop, I got coffee, warm, present, all these things. So basically, it's like all of those do describe it. And no matter how or anybody thinks of it, it could be different. So that's kind of how AI does. It's like organizing things. And if we go back and look at the top question for the answer we saw, guess what? They actually mentioned how sorting algorithms can be used in different ways. Now I'm going to actually go back. Give me a second. I do want to actually go back and show you that. In the original question, they asked, there are multiple ways to solve a problem, hence algorithms. Each algorithm has its own significance and beauty in terms of space, RAM space, used by it called space complexity, time taken to run it called time complexity, and complexity to implement it, etc., etc., etc. We use different algorithms for the same problem depending on our requirement. An example, sorting algorithms. There are lots of sorting algorithms. Quick sort, merge sort, bubble sort, bucket sort, insert sort, selection sort, etc., etc., etc. Just think of the time when someone faced the problem for the first. Alright. You get what I'm saying? So even they saw the AI is 99% sorting. And that's what this is. Ways to label that sortability. Because like I said, by saying that coffee cup, table, warm, presence, that scene, you can say that to anybody. They all get a billion different scenes to think of. Not one of them has to be the same scene, ever. It seems almost infinitely different. Well, welcome to AI, bro. Now you know why sometimes you can ask AI the exact same for the exact same picture and get it two different ways each and every time. Because it's just getting these labels and then trying to picture what scene might be from those. Oh, let me go back and make sure you have the link to this. Here we go. before we go to the next one. So here we have sorting algorithms, actually supervised and unsupervised learning. Yes, it looks like sorting algorithms. Okay, so I've mentioned this before in different streams, but it's about time we talk about this. Yes, there are two ways to do this, supervised or unsupervised. Now, in many points, this is really like 5, but let's get real simple with it, okay? Supervised, although it may have human interference, it can be any system that relays positive or negative feedback, while unsupervised expects to get things right slowly over time, on its own, without any additional feedback of any kind. To many, this seems strange, but unsupervised oftentimes shows bias in code, as well as tends to be more accurate over time versus the other one. So this works in a strange but simple ideal. If you have two humans that have no differences other than they are not the same person, so equitably in every measure and aspect, you give them, both these people, the exact same goal with the same reward in mind, but one of them, you give a little instruction packet to help them along. Okay? Regardless of what happens, the one with the packet has an image or something simple, like words of a simple task, something to guide them along with each step of their way. They will eventually get there. You already know it. However, the other person, if the goal is easy, they will get there really quick. First time, most likely. But if the goal is hard, it might take them a lot longer to get there the first time. It might be trying over and over and over until they slowly just cancel out the other options and get there. So, while the first will try to have the first one will never have to retry something. It will sit there and wait and make a decision until it knows it's made the correct decision, where it doesn't have to retry or pick the other. So it can always just continue moving on. It allows it to like clear its old memory, different things it might not need to know moving forward, whatever. Kind of like forgetting the world behind you at any point in time. So, if an AI is told, for example, draw a square 1 billion times, it hopefully should be able to draw a square. But however, if you told it the first time and it got it, you don't need to keep telling it to draw the square. So, unsupervised works on this ideal of, if the model is good, it won't need to be told to do it over and over and over. It'll just do it once, boom, done, good to go. And so that means it won't need to adjust. So basically, before it does anything, it will adjust itself to a model and then continue. Now, if it outputs badly though, then eventually from being prompted to do it again and again and again, it adjusts every step and it'll be forced to adjust more and more and more. And then, so eventually, it'll find the medium and get there. So supervised may only adjust once and it's completely done for that step, task, or second. While the other is probably going to be doing it a bunch of times. Many times. So, many times a little bit. So after the human input is there to help it shape its model, it's just going to go over and over and over and over and over until it, the more times it's asked to do it, the more times it's going to reinitiate the iterations until it finds a spot that works. So I hope that kind of helps make some sense of, imagine just picking one of the like a square, circle, or triangle at a time, and then going, what is it, and putting it down until you eventually figure out there's 3 different versions and you get them separate. You might have 2 piles at first, and then you turn it to 3 piles. So you start off with 1 pile, turn it to 2, and then maybe turn it to 3, and that's unsupervised. But you pick up each one, and then you look down in the book, and it either looks exactly the same or don't look exactly the same, and then you separate the pile that way. That's supervised. So imagine that, like the one right here over my shoulder with the question mark, he picks one up and he looks at something. If it looks exactly the same or near exactly the same, it puts it in 1 pile. If it don't look anywhere near the same, it puts it in a second pile. Boom, ends up with 2 piles. While the other one just picks up one, then picks up another and looks at the 2 of them. Do they look the same? Nah. Put them in 2 different piles. And then eventually ends up with 2 piles with some stuff that kind of looks like it and some stuff that kind of don't. And maybe the first time around, it gets all 3 piles. So that second, the unsupervised, it will have to reinitiate this until it figures out that all of them, when it picks up all the one in a pile, They all look exactly the same, no matter what they look like. So it has no information but learns from the simple little mouth. And I kind of pointed out earlier, there's a strange occurrence where you get a bunch of bad negatives. Eventually, you end up with this medium of correctness. And it's kind of like, it's not always so obvious. Let me explain this a little more. Alright, let me highlight this so I can see it better. There are times where we know a specific model just works. Maybe it's math related, something that's simple, more binary or trinary, or in other words, there's no gray involved. Well, we can let humans tell us when it's wrong. Then to do a negative model and save the previous model that is adjusted by that negative model, and then that will just adjust for that specific human, allowing for human adjustable models. So that's probably the most number one reason why supervised is used. Human adjustable models, where it's like adjusted for the human automatically. However, there are some models, like art and music models, that there are way more gray space involved, where you probably don't want a billion negative models. It could be a lot more problematic. A strange occurrence with negative models is that when you stack them all on top of each other, all negative models, you'll eventually get a positive model from essentially over half of the possible negative models has been stacked up or so. This strange occurrence is because over time, all these negative models, they end up with this strange where like they build up a reinforced areas of like negativity and positivity. And then you just basically flip it from positive to negative like you would in art, and it's the exact thing. It's normally what you're looking for. So, and it's not very obvious that that's a thing that you can do. Just take all these bad things and just flip it from positive to negative, like from white to black, and then boom, it's 100% different. But that's kind of what a lot of the unsupervised model works around with. Why unsupervised learning is still kind of important. It can do things with simple little bits of information, like I said earlier, until it can pick up all the ones in one pile and they all look the same. It'll keep sorting it. Alright, I hope I got the point across there. It's a little bit more complicated, but it's very important, because these are like, when you're starting to build your own AIs, this is one of the number one things that gets people stopped. And there is ways to put both these together. Definitely. Alright, going into it. Gradual descent. So gradual descent, like using this graph, for example, it's based on a goal. With this one has 3 starting positions for finding the simplest or fastest route to the goal, which is the center. This is a prime example of how AI uses data graphs as a visual representation, even if it's not a visual problem. For example, this could be how NPCs find its way to you in the game. Or it could be for determining differences in pixels in an image section for finding like pixels. You'll notice one traveling dot stops and ends, never reaching the center point goal. That's like finding a pixel not near the same color as the other ones you're looking for, or not finding the right person, the NPC finding the wrong person, you know. So to speak, this is used for practical determination methods on which model might be to find a solution. And now it knows how to break down its possibilities. It knows how to break down what it might need to do, or out of the things, what might be the right one, so it has less than it needs to try. And this is a way for AI, for example, to test itself, test things before it even does anything. One way, unsupervised, can be more logical, and one way, supervised, can be a little bit quicker. Now, I will admit, this is one of my favorites. This is like the one they taught me in school, bro. Simple Bayes or Bayesian network. This is often how prediction algorithms work. This is taking in what is the likelihood that the grass is wet because it's either potentially rained or sprinkled. A classic binary problem, but seemingly endless ways to determine the probability. But anyway you cut it, it should end the same. And yes, it can be both in this case. Let's have a spot where they can be both. Yep. Alright, so we're just going to keep going because that's pretty simple, I think. Now, for example, here is a a clustering. And this is, for example, Old Faithful data showing the duration of spray and delay to get that spray. There are some strange correlation here where the longer sprays take longer to show up, while the short sprays happen more often to other sprays. Now, it doesn't show it in the order they happen, but definitely does show this major correlation. We can also see there's a lot more larger sprays than shorter sprays. So from this, we could easily find out where the most of the data is, how if it starts getting where there's more short sprays and less long sprays, it would show easily. You could be doing models that would show that change. So there are definitely ways for AI to use this and with other algorithms and correlation to track changes over time. Also track differences between multiple different things, or the same thing in this case. So here we have neural networks. You may have guessed we have been sorting data this whole time. This is a neural network version. So yeah, the first was how things, the very first one we looked at, go back to it, is like how things are broken down, organizing. And then the second image was ways of organizing and checking that organization. The third one is basically the best decision making by a data graph to concluding or to do a sort. So before you ever do it. This one is making the best decisions based on probability. And this one was best decisions with data on a graph. So now this one, network decisioning, yeah, network decisioning. So after seeing the others, it's kind of easy to see what's up. Like the hidden bit in the models here is that the AI leverages everything against, which then it gives some kind of output. And the output isn't always the same as the input. Often the input is much, and often the input is much, but you get one or fewer outputs in consideration to the amount of inputs. And a good point here is it doesn't matter, like they used to say, it doesn't matter how much you input, you'll get at least 2 outputs. And there are some AIs that it's not true, but there are some AIs designed to like use the 2 outputs to cancel out to find the in-between medium of those 2 to then give you a single output. So that does exist. Alright, hierarchy. So AI hierarchy, and really it's more or less how we perceive it to be in reality. Think of it like if AI wants to do anything in its deep learning database, like a model, it needs to go through that machine learning, the stacks of model outputs that the AI uses as adjusters to its model. So if anything, this shows the database hierarchy. So when you use AI and you have to go through these type of strange one-way actions, maybe this will help explain what that you're actually doing to get you to your end goal. If anything, this should show you at least that AI isn't just randomly doing something and not randomly pulling from memory. It has rules it follows, just as the people working with it and coding it have to also follow. It's like a natural rule, so to speak. So reinforcement learning, perfect, right? Which is a type of supervised learning, and this is often the one humans prefer. The human bias almost always gets in the way with these. I think it's, if anything, this is the most straightforward one to see. AI does something, someone views it and rewards or tasks the AI until desired output is viewed, and then reward is given and then looped again. Indefinite, or it could be. Always could be. Alrighty then. So, in case you ever want to learn more about any of these independently sectioning parts of AI, you can always use this as reference material. A lot of these pictures came from here, in case you're wondering. But we're going to keep going on. Uh-oh. Alright, so it looks like I might have lost my thingy. Let's see if I can renew it. There we go. So here we are. And I think it's oddly important that, like, the AI boom was because of LLMs. Not many people realize this. Let's learn a bit of history. In 2017, the transformer architecture was proposed by Google researchers. It exploits an attention mechanism and became widely used in large language models. Large, because they did exist before that, but not very long before that, in my opinion, like the ones we're used to now. Based on the large language models based on the transformer were developed by AGI companies, OpenAI, JBT3 in 2020. DeepMind released Gato in 2022. These are foundation models. They are trained on vast quantities of unlabeled data and can be adapted to a wide range of downstream tasks. So they can be given just raw data and they can figure it out. These models can discuss a huge number of topics and display general knowledge. The question naturally arises, are these models an example of artificial general intelligence? Bill Gates was skeptical of the new technology and the hype around AGI. However, Altman presented him with a live demo of ChatGPT-4 passing an advanced biology test. Gates was convinced and made in that year, 2023. So Microsoft's researcher tested the model with a large variety of tasks, concluded that it could reasonably be viewed as if an early, but not complete, so it's still incomplete version of AGI. I think that's kind of important because a lot of people were using Bill Gates' turnaround, so to speak, as oh, we have AGI, but even he's saying no, this is not AGI. Even I'm saying no, this ain't AGI. There's a lot of people saying no, we don't have AGI, and AGI is the point where we are not actually needed, and that's what a lot of people don't realize. Well, once AGI is created, there ain't no going back. There's no turnaround. It's done. So that's why we know we don't have it yet, because it's not doing things yet that we can't control. I mean, like, it can, but I mean, like, we still have control somehow. In 2024, though, OpenAI O3, a type of advanced reasoning model developed by OpenAI, was announced. On the abstraction and reasoning corpus for artificial general intelligence, the ARC-AGI benchmark developed by Francois Chanra in 2019. I'm sure I said that wrong. Francis Chanra. I'm sorry. I'm not good with French. Or whatever that may be, because it could be Portuguese. The model achieved an unofficial score of 87.5% on the semi-private test, surpassing the typical human score of 84%. The benchmark is supposed to be a necessary but not sufficient test for AGI. Speaking of benchmark, Gale has said, you know AGI is here when the exercise of creating tasks that are easy for humans but hard for AI becomes simply impossible. Now, we haven't actually got there yet. We still have tons of tasks that are not easy for AI. So we're not there yet, but they are for humans. As far as that is. Alrighty then. Alright, so symbolic artificial intelligence. This is the type of AIs I normally deal with. Old school AI. AI based on logic problems and sorting based on how humans would do that. And in a way for humans to be able to read the outputs, models, results, etc. That's something many people don't get. Oftentimes AI models nowadays are hash that is full of information that humans just couldn't make heads or tails of because it's intended for its machine learning interpreter to discrete some of this, to use some and then pass it down to the database to obtain what seems like random bits returning. Then that is interpreted again by the machine learning to then relay to the humans via the LNM or Canvas sprint to explain what an output actually is. So the symbiotic AI is nothing like that. It's one. This one is more like if this is like one type or one part of the previous AI, but still not quite the same. Better way to explain it. Previously, it was more straightforward. It's simple. More individual solutions need to be coded or designed for traditional AI. And current models are a lot more complicated. it does more or less also, so to speak. Um, so previously you needed a model for every little thing. Now you kind of just have like general sets of models that can be used for lots of things. And I have here an example of how one model can be used for two exact same things, which is something we did early in AI art. Like really early was this type of stuff we were doing. So we can be doing stuff like determining what my next shopping list may be, or what I might need on my next shopping list. This may be not seem like the same data set, but as like AI art, but my same data, my shopping list with the pictures to help me find the object, now lets me make better AI art over time. But previously, these could not be used as the same models or databases or interpreters. The things have definitely changed where I can take pictures of my stuff and put labels what they are, and then have it set up to where when I'm running low on this stuff, it knows to tell me to get more of it. Well, that can also be used to make pictures using this stuff because it has it in deep memory in a manner where it can be used agnostically. So, nice. So, symbiotic artificial intelligence, known as classical artificial intelligence, is the term of the collection of all methods in artificial intelligence research that are based on high-level symbiotic human-readable representations of problems, logic, and searches. The symbiotic AI paradigm lead to the seminal ideals in search, symbiotic programming languages, agents, multi-agent systems, and symbiotic web, and also the strengths and limitations of the formal knowledge and reasoning systems. Like, we couldn't get to where we are in AI without symbiotic AI to get us here. Creepy. Alright, we gotta talk about it. Transformer. So, if we look at here, we can see there's stuff being inputted down here at the bottom, there's stuff being inputted at the sides, there's stuff going back and forth, and we can sit here and talk about this for a good little bit. I ain't really going to talk about it. I'm just going to basically show you that most times you're giving it two things and expecting one. So you're giving it multiples and expecting a single output. Now these could be the exact same thing, but it's just, there's a lot going on. I just need you to understand there's a lot going on, and the way it does this is it takes the thing and it separates it into multiple idealable tasks or ideals or concepts or solutions or whatever, and then cuts those heads off one at a time, like a idea to fork its way down to a single new whatever, and then it keeps doing that over and over and over until there's nothing else left to do, and then we can basically conclude 99% of believability that this last solution is a prediction or whatever. Yeah, it's confusing, but it's kind of like quickest way to find the average is all they're doing. They're finding a quicker way to find the average. So here is about Transformer. Transformer is a deep learning architecture that was described by researchers. We already kind of explained that. About the multi-head attention mechanism, which was proposed in the 2017 paper. Attention is all you need, in case you want to learn more on that. Text is converted to numerical representations called tokens. Each token is converted into a vector via lookup from a word embedding table. At each layer, each token is contextualized within the scope of the context window with the other unmasked tokens via parallel head multi-attention thing where they cut them off one at a time to find the right one to be used and amplified. So that way the less important ones can be diminished. That's basically what the best way to describe it. So basically this allows for much of the old work to be simple lookup tables, and then after that the attention method really is just a faster determining of the possible endpoints to pick the best possible ones to get down to, like I said, finding the average faster. Very genius actually. So decision tree learning. So this is probably my favorite type of AI algorithm, to be honest with you. You may have heard of it. It's called Symbiotic Transformer Decision Tree AI. I'm that kind of guy. And to be honest, many AIs use a form of decision tree learning or overviewing, and that's normally called supervised learning, just so you know now. Deep learning is kind of something humans do without realizing it. It's why we see things in clouds, or how come we can spot the leopard in the wild even though it has camouflage. Deep learning takes the input, finds the common lines, finds unique connected lines, and then finds the shape from connected lines. Wait a minute. Yep. Okay, alright, I see. Let me just keep going. So, now in this case, okay, there we go. Yeah, and then it finds the next connected lines, and that is a new directions before the three major parts that it uses. Now in this case, they don't know how to show the AI is concluding that to form that it's given. Alright, so somehow I have a section of information that got missing. I wanted to make sure that I was in the right spot. I am in the right spot, but it is talking about deep learning, and basically there's not a whole lot to say about decision tree. It's one of my favorites. It's very simplified. It's all about breaking stuff down most by label and giving a problematic or probability at most of what might get you where type stuff. So we don't really need to go into it. We kind of really explained a lot of it earlier, but this is basically what I was just kind of explaining. So deep learning takes the input. Let's go to the beginning. So here's the input. These three shapes. Takes the input, finds common lines inside these inputs. These are all common lines in the input. So all these two lines are common, are the most common two lines in this. These two are the most common two in this. These two are the most common two in this. But also these. Oh, hold on. Sorry. Those first two lines are the most two common lines with the elephant picture. The second two lines are the most common two lines with the kangaroo picture. The last two lines are the most two common lines with the penguin picture. But also, the second and third lines are two lines commonly available in both the elephant and the kangaroo picture, while the fourth and fifth lines are both common lines found between the kangaroo and the penguin picture. And so, where's my thing? So now, it then finds connected lines to those that are unique compared to the other pictures. So we can see the elephant is getting more of a trunk and ear shape. We can see we're actually getting like a body and a leg shape, like from like the kangaroo's arm. And then near here, it's starting to get weird. Believe it or not, those are only one of those was created from this image below of the penguin, which was also created from the kangaroo. But the other two have nothing to do with this first one. And because there are such differences, it can now conclude this penguin is not the picture. Now, believe it or not, at this point, it's also already concluded the kangaroo is not part of the picture, but we can't really tell that. So we go up and we see the three things. Now, this is the spot that it's able to go, oh, the kangaroo has nothing to do with this either. Because it put these together, like minds together, and it should have show something from one of the pictures, and it is showing an elephant. Now, if it fits within the shape, it knows, yeah, most likely that is what it is. And if you go down here, it does mostly fit in. The elephant does mostly fit in there. Yeah, most likely it knows what it is. Deep learning is this fun system that allows it to do these things. It's a subset of machine learning that focuses on utilizing neural networks to perform tasks such as classification, regression, and representation of learning. The field takes inspiration from biological neuroscience, and is centered around stacking artificial neurons into layers and to training them into processing data. The objective deep refers to the use of multiple layers ranging from these three to several hundreds of thousands in the network. Methods can be either supervised, semi-supervised, or unsupervised. But they're not going to have to be mixed. It's basically a mixture of anything, right? So some common deep learning network architectures include fully connected networks, deep learning, a bunch of different crap. These architectures have been applied to fields such as computer vision, speech recognition, natural learning processes, machine translation, bioinformation, drug design, medical image analysis, climate science, material inspection, board game programs, and the list goes on and on and on. Cool. Neat. So deep learning is kind of like this process system that gives AIs power. Power of understanding, too. I don't know if that was really described. Power of understanding. Wait a minute. Seriously? They give me these tables? I have notes here saying there was a table describing, but I guess it's kinda, yeah. Does this kind of help explain how you're giving it a bunch of inputs and it's making decisions based off that? I hope so. Maybe the picture kind of does it, yeah. Good one. Alright, so the Bayesian network. I think I'm missing something. My bad. My bad. I just got. Right. My bad. My bad. Bayesian network. We did look at a picture of this earlier. So it's also known as Bayes network. Blah blah blah. It's probability graphical models, representation of variables and their common dependencies. Also via directed algebra graph DAG. I wanted to get this out here because there's a lot of cryptos out there that are using DAGs and they're all like, oh, so great, and it's like, bro, they're using DAGs to solve the Bayesian problem, but the Bayesian problem is represented as a DAG. So anyways, Bayesian networks are ideal for taking an event that occurred and predicting the likelihood that any one or several possibilities were the contributing factor. This is basically finding factors of, it's like, why did it rain? Remember? Or why is grass wet? So here is Bayesian programming. Although I do not want to go over this page, the next two images are from here and are about this because the programming of logic determination is its own issue, and like all parts of AI, has no wrong way to do it really. So here's the first image, and as you can see, this is just a generic program, Bayesian program. The breakdown of the tree of how it's going to do things. It's going to have a program, it's going to have descriptions and answer a question or have a question with specifications, and it's going to base identifications on that, and then it's going to go into detail on those of what they might be. So going on to show you an example, this is spam detection. This is the program for spam detector. Right here. This is the logic. And we won't go through it all, but you can basically see it has outputs or endpoints that end with either false or true, with a percentage or amount. Some of these are complex, like not really a percentage right there, is it? It's just more math. But yeah. So, evolutionary algorithm. This is basically inspired by AI algorithms, and it's pretty kind of straightforward. So, reproduction is essentially elements of the biological evolution in a computer algorithm in order to solve difficult problems, at least approximately, for which has no extract or satisfactory solution methods that are known. So, it has no known solutions. These are for things that we don't know how to solve, that we imply a biological similarity to get to the endpoint. So related techniques and other global search methods. Basically, there are some other proven and widely used methods for of nature inspire global search techniques such as mnemonic algorithm, a hybrid method inspired by Starson's notion of a meme. It commonly takes the form of population-based algorithms, frequently in EA, coupled with individual learning procedures capable of performing local learning environments. Emphasizes the exploration of problems to specific knowledge and tries to orchestrate logical global search in a synergistic way. Also, cellular evolution of mimic algorithms use a topology neighborhood relation between the individuals of a population, or restricting the mate selection, and that reduces the why do mates mate type thing, right? But down to the cellular level. And then there's ant colonial optimizations that are used a lot of times with graphs and such. Then you have particle swarm optimizations, multiply used for animal flocking and stuff like that, but also suited for numerical optimization problems. And then Gaussian adaptations, which lots of people know that as like the Gaussian blur is a Gaussian equation to get that. So based on information theory comes the Gaussian adaptation, which is mostly the human thing that most people recognize. Cool. Woo. So I mean, so far all of these work fairly different. And I hope that you're getting almost all of these work way different from each other. Okay, so the hybrid intelligence system donates a software system which employs in parallel a combination of methods and techniques. Okay, so these often come to what you're seeing here. In my perspective, this is more of a philosophy of AI and less AI. But these are real systems, these are real types of AIs, and many of these are just about synthesizing human-like outputs. That's, I think, the most important part here. These are all about synthesizing human-like outputs. From the cognitive science perspective, every neural intelligence system is hybrid because it performs mental operations on both the symbolic and sub-symbolic levels. For the past few years, there have been increasing discussion of the importance of AI systems integrations. Based on notations that have already been created, simple and specific AI systems, such as for computer visions, blah, blah, blah. And now in time for the integration to create broad AI systems. Proponents of the approach are researchers such as Marvin Minsky, Ron Sun, Aaron Solomon, Angela Dali, and Michael A. Arab. Cool, or Arab. I'm not sure how to say that. Okay, cool. Alright. Finally. The good stuff. Alright, so I think in the last episode we were trying to find common solutions to AI integration. And we did showcase in at least one of the previous episodes an AI that helped handle all of this, specifically what you're seeing right here. Because you will see very quickly, it's not even a single programming language. It's normally used for a full AI system. It's normally a bunch of programming languages, a full AI system. And on top of that, you also need normally more than one system to handle everything because there's so much going on. Sometimes the algorithms are very complex on hardware, or they're very complex and hard on hardware. So sometimes you need more than one hardware to do each individual algorithm or step in the algorithm to ensure that it has room to do it. All right. In my opinion, AC is the way of AI. More and more basic AIs nowadays already are AC. That's AISI, or this Artificial Intelligence Systems Integrations. And we will, for now on, be AC because they work how humans expect them to work. Well, at least normally they work how humans expect them to work. And that's why I think they're going to be the future. The core ideal of AC is making individual software components such as speech synthesizers interoperable with other components such as human common sense databases in order to create larger, broader, and more capable AI systems. The main methods that have been proposed for integration are messaging routing or communication protocols for the software components used to communicate with each other. Not too long ago on a different episode, we did talk about how there is a way for AIs to teach each other. Like one AI can teach another AI its back end. That's one of the things we're talking about. That picture. A lot going on here. I mean, not a lot in the Wikipedia page, but a lot on this topic, a lot on this page that easily take advantage of paying attention. Alright. Today is another one of those. The point isn't simple and clear. Let me try to clean it up. Most people running AI have no clue how or why it works. And that is kind of how it should be in many perspectives. AI is simply trying to get to a goal. There's many ways to contextualize, idealize, visualize, compare to, and compare with, and so on, that if anything, getting different AIs that don't work the same to work together, like the integration part and AC that we just highlighted, are the best forms of AI, for the AI has more than one potential to consider. Even every major step in AI from a user perspective would have been seemingly minor each time. The first idea of having a method of handling any problem with as little equations as possible started AI. Then having a method to conclude logic determination, in which is also in a manner that humans can review the results, it kept it going. Then having the ability to talk to AI or software as if it was human in plain text was what pushed more. And to be honest, the only next major advancement is in the minor workings of handling these different possibilities for the AI to pick from, as well as the minor workings behind the scenes. If you was to go back and rewatch today's episode, you'll probably get a different perspective of after going through it this first time, because some of the nuances you just glazed over the first time will appear more bluntly to you the next time. And if anything, that's much of what AI is like. Today's episode was designed in a method that if you rewatch today's episode, you should get more from it each time. Once you don't get anything new from watching it, again, dive deeper into the QRs per page, starting with the previous episodes of the miniseries. And then basically every time you think you have watched things or read things and redo things, just redo it again until there's nothing more to be relearned or learned or found or discovered. That's the life of AI. Learning what's obvious each time only, but as new things are in the back of your mind memory, new obvious things appear that were not obvious before. Kind of just like randomly while going back through it all again. Like you just kind of randomly pick up things. Like when you watch a movie 5 times, 5th time, or 6th time around, you're like, oh wait, I didn't notice that little Easter egg in the background. That kind of thing. That's AI. That's all AI's life is like. It's constantly relearning. I don't know, man. To me, kind of sounds like it sucks in a lot of ways. But if anything, now maybe you might understand why you might need to look at your AI many times. Why you need to do different things, or why this or that. It might seem stupid, sure. Guess what, man? Sometimes stupid is what stupid does.
Yo, did you think you know? Did you think you hold? Did you think something new? That's the goal, to see from a new degree and get the change your mind needs to find something new. Life suddenly is easy for many, but when a wall appears, sometimes up is all you see. So let 3D guide to the side, yo, where there's a door though. Just be careful on your way out, for the first step is a do-see-do. A little bit honest with something different, it's almost like he's something else. And regardless of maybe, perhaps it was that missing piece you was needing. Maybe it was that simple message you was searching. Definitely it's just in different times, a defraying our mental mind state, separating us from our own mental mental mind tank. Boom goes the blast of thought. Boom goes the last spark with pot. Boom goes the mental mind tank. Don't your perspective hit on the way out. Don't let your directive stop you when you doubt. Don't let the dire detection stop you from being getting excited, so the photons are delighted. Don't hesitate so we can line up the hash rate. Let me surmise the time, submit the rate, and reduce the fakes while we mine our major banks. Crypto technology like cryptographic money, while hashing your life into a set of QRs. It doesn't matter, cause this was 3D changes perspectives. Thank you for joining the show. Please return next time for a new roll of perspective. Thank you for joining the show. Please return next time for a brand new perspective. Of perspective. Thank you for joining the show. Please return next time for a brand new perspective. Thank you for joining the show. Please return next time for